Okay, so in the next few videos, we're going to be talking about differential equations. And differential equations are pretty useful in a lot of different applications, and we're going to see what they can help us do. And so I think it's pretty helpful to start by just defining what a differential equation is. And in general, it is an equation that contains derivatives of one or more dependent variables with respect to one or more independent variables. So essentially, why do you study differential equations? And so we've probably seen, and let's just give an example. So this is a differential equation, dy over dx is equal to 0.2xy. And we see that y here is our dependent variable, and it's dependent on x, which is our independent variable. And then we have some sort of expression relating the derivative to, both the variables. And so it kind of matches what the definition we have over here. And with differential equations, we're really focused on trying to find a solution that sort of agrees with the differential equation that we have over here. So that's essentially the goal with most of our applications. And we'll see as we do learn more is that usually there's one or more solutions, right? So the interesting thing is there are usually more than one solution. And then solutions are valid on some interval. Okay, so we're going to be dealing with these properties that, we have solutions, but they only work for certain intervals, or they're only, valid on certain ranges. And, we need to really figure out which one is applicable to what we need to do. And so that's sort of the intro to what a diff EQ is. Probably seen them before. And so I think we'll spend time just going over some terminology and definitions, and then that'll help build on the future. So the first thing that we have is the types of differential equations. So we have the first type is something called an ordinary diff EQ. And so an ordinary diff EQ is just a diff EQ that contains one or more dependent variable with respect to a single independent variable. And so with these, you're only really dealing with regular derivatives. So some examples are dy over dx is equal to e to the power of x minus 5y, right? So we have just one dependent variable, one independent variable. Another example is d squared y over dx squared is equal to dy over dx minus 6y, right? You have higher order derivatives, but again, just one independent and one dependent. And then if we had something like plus dz over dx, again, as long as we have only one independent variable, these are ordinary diff EQs. The other type is something called a partial differential equation. And here now we can have more than one independent variable. And so we can still have multiple dependent variables, but now we are dealing with multiple independent variables as well. And so you'll usually see like partial derivatives, like the partial of u with respect to the partial of x, plus like the partial of u with respect to the partial of y is equal to like 0, for example. And so now we have more than one independent variables, and then you can just augment this and have multiple dependent variables as well. So something like this. And this is like much more complex than dealing with these. So we're just probably going to be focusing on the first one. But that's the first classification. The second classification is the order of a diffie. And so an order is just the highest derivative. So previously we saw we had more than like just the first derivative. And so example is like if you have d squared y over dx squared plus x times dy over dx squared is equal to 4, right? Don't get confused by this term being to the power of 3. The order of this is just 2 because our highest derivative is a second order derivative. This derivative is just to the power of 3. So you can like treat this term as just like another variable if that's confusing. One other thing that we're concerned with when we're dealing with diffie-qs is whether or not a diffie-q is linear. And this is very important because if a diffie-q is linear, we can utilize a lot of like special properties and it makes our lives a bit easier. But a nth order diffie-q is linear if we can write it in this form. Where we have some function related to x and then over dx10 plus a n minus 1 x d minus 1 y over d. So essentially what we're saying is we have a linear, or our differential equation is linear if basically all the higher order derivatives, they're only sort of multiplied by a term that is a function of at most x, right? So this term, this coefficient doesn't have to be linear, right? It can be something like e to the power of x or like x squared, but the actual derivative has to be linear. So if you had something like dy over dx squared times x, now that's not linear, right? And then this function as well can be something general. So to put it more concretely, these are linear diffie-qs. Y minus x times dx plus 4x dy. Since both the dy, or like the term related to dy is multiplied by a function of x, and then over here y is also just multiplied by a function of x. So we're fine there. And then another one is like y double prime minus 2y prime plus y is equal to 0. Again, none of these terms have any special thing going on. They're just multiplied by some functions. And then a final example will be like d or dx x dy over dx minus 5y is equal to e to the x, right? So even though this term is like this function over here is not linear, we're only worried about the y terms being linear. And so if it was like e to the power of this, then it would be nonlinear, right? So that's an important caveat. And so to really just nail this point, let's look at some nonlinear functions. So nonlinear diffeeqs. One of them would be 1 minus y times y prime plus 2y is equal to e to the x. So here, y being the dependent term, we have a coefficient that depends on y. So coefficient that depends on y. Hence, it's nonlinear. Another one that's a bit more explicit is dy squared plus sine y is equal to 0. And clearly, like, this is a nonlinear function. So our diffeq is nonlinear. Okay, so hopefully that makes sense. And so those are like the main properties of diffeqs. And so let's now talk about like verifying a solution. Verification of a diffeq. So verifying a diffeq is just saying that we know that diffeq is valid for a certain interval. And then we're claiming that we have some function phi of x satisfies our diffeq. So essentially what we have to check is that this function does satisfy the given differential equation for all the terms, inside the given interval. Because recall that when you're finding the derivative of a function, right, it's over a continuous range, and so that's why we have to make sure that the diffeq is valid for all the points inside of the equation or inside of the interval. And so one example would be like we're given dy over dx is equal to xy to the power of 1/2, and then we're saying that the solution is y is equal to 1 over 16 x to the power 4 on the interval of all reals. And so how do we verify this? Well, we're given that this is the explicit solution, so let's just find the derivative. So dy over dx is equal to 1 over 4 x to the power of 3, right? And so over here we're given that that should equal this. So we know that y is this term, so y to the power of 1/2 is equal to 1 over 4 times x squared, and then we multiply that by 1 over 4 times x to the power of 3, and so we end up getting 1 over 16 times x to the power of 5. We're multiplying this by x, just x. So we end up getting 1 over 4 times x to the power of 3, and that's what we validated over here. So this differential equation is valid. And the part about this whole range is that because we just took the derivative, we didn't just take the derivative on a specific range. So like trivially it makes sense that our diffeq has equal values for the whole range. And so we can conclude that this is a valid satisfaction. Another example is we get y double prime minus 2y prime plus y is equal to 0, and then we're saying that this is satisfied by y is equal to x e to the x. So let's do the same thing of finding the derivative of our explicit function, and so we'll get something like 1 times e to the x plus e to the x times x. And then y double prime is equal to e to the x plus e to the x plus e to the x. So 2e to the x plus x e to the x. And let's just put it into our diff EQ that's been given to us. So 2e to the x plus x times e to the x minus 2 times e to the x times x plus e to the x plus x times e to the x. And we need that to equal 0. So these two terms cancel out. And then we have, oh, sorry, I meant these two terms. And then over here we have minus e to the x times x plus x times e to the x. And so we know that that is 0. So this is valid. And again, we didn't constrain the range of x to a specific interval. And so this should be satisfied on our whole interval. And so that's therefore our if EQ is valid. And now, like one thing, like if it said, if the interval was like given as like -5 to 5, right? It would, this diff EQ would still be valid because it's a subset of our original large interval, right? So that's, I guess, something to keep an eye out on. Okay, and finally, we're going to be talking about something called an implicit and explicit solution. And this is probably something that you're familiar with already, but an explicit solution is just, so we'll talk about explicit. Solution where dependent variable solely is expressed in terms of the independent one. So something like y is equal to x times e to the x, right? On the right hand side, we only have independent variables, and then that's how our dependent variable is defined. Implicit is basically where the solution can be also defined in terms of the dependent variable. So if we get something like x squared plus y squared is equal to 25, right? Our independent variable is not, or dependent variable is not separated out, right? So our whole equation is defined in terms of both the dependent and independent variable. And so we can say that this is an implicit solution, or like let's verify that this is an implicit solution of this dpq, right? And again, it's just very similar to what we did before, but now we're just going to implicitly differentiate it. So we get like 2x plus 2y dy over dx is equal to 0. And then we just take stuff to the right side, and then we get minus 2x divided by 2y is equal to dy over dx. And so we know that that is minus x over y. And so we validated this being the solution on the, and then I think the range was like -5 to 5. And we know that this is good on that range because of the fact that this curve, when we graph it out, we have a circle, right, between the range -5 to 5. And so we can just either take the top half of the circle or the bottom half of the circle, and we know that we get different diff EQs or different explicit equations for that. When we solve for y, we get like y is equal to plus or minus square root of 25 minus x squared, right? And so we know that we have a curve that, an explicit curve that satisfies this on this range. And if the range was bigger, right, like if it asked for like -7 to 7, for example, then we could not satisfy it, right? Because there does not exist a curve that has this diffie. So I think hopefully you notice that the relation between the interval and the explicit solution are very closely intertwined, and so it's very important to make sure that the solution actually matches on the interval given, because otherwise sometimes you just don't have a explicit solution that matches on the interval for a diffie. So that was the properties of differential equations. I think the main takeaways are like, for a differential equation, we have potential explicit solutions on certain ranges. And then given the range and the solution, that kind of defines whether or not, that equation is valid or not. Okay, I think the last thing that I wanted to talk about is this idea of a particular versus singular solution. So a particular solution is a solution free of arbitrary variables is a particular solution. So remember when we found the integral of a certain function, we added like the plus c, and so that's like an arbitrary variable, right? So similarly, we can have multiple explicit solutions that can satisfy a differential equation, and an explicit solution that doesn't contain that arbitrary parameter is one that is called like a particular solution. So if we said that a solution is like 1/2 x squared, that would be particular. If it had like a constant c attached in front of it, it wouldn't be particular. Okay. And then a singular solution is a solution that does not belong to a family of solutions. So if we had something like c times 1/2 x squared, okay, we can remove the 1/2, but c times x squared, the family of solutions is like all the values of c that kind of satisfy this, right? So we could have something like 1/2 x squared or 1/4 x squared. But if we only have one particular value of c that kind of satisfies the equation, then it's like a singular solution. So for some reason, y equals 0 is a solution. Like, if you're attaching a c anywhere, it would still be y equals 0. And so you'd call that a singular solution. There isn't a family of constants that we could like kind of shift up and down the graph to still satisfy what we have. And so those were like two classifications of solutions as well. And so yeah, those are properties of diffie that we'll be dealing with, and hopefully as time goes on, things will make more sense with this.